Good morning. I'm Stefan Werkstetter, VP of Sales at EPC for EMEA. Welcome to today's webinar, GaN First Time Right PCB Layout Rules for Converters and Motor Drives, where we will cover essential guidelines to ensure your GaN-based designs succeed from the start. Before we get started, I would like to go over a few housekeeping items for today's event. You will have the opportunity to submit text questions to the panel by typing your questions into the Q&A feature at the bottom of the screen. You may send in your questions at any time. We will collect these and address them during the Q&A session at the end of today's presentation. Now I would like to introduce our speaker today, Tiziano Morganti, who is our staff field application engineer here in Europe. Tiziano, the floor is yours.
Good morning. Welcome to everyone. Let's start with the presentation. Let's have a look to the what are the topics today. So we will talk about the parasitic inductances and their impact in the switching of a converter. We will do some comparisons of layout designs. We will go through how to design a low inductance layout, including gate circuit. We will have a look to common mistakes and how to fix them. We will talk about a parallel design example for DC-DC converters. We will talk about PCB properties and requirements for EPC FETs. And we will have a final look to how the motor drive requirements are different compared to the DC-DCs and how this affects the layout. So talking about the parasitic inductances, we consider an half-bridge circuit with a gate driver. And the following few slides are an extract of our how to GaN 5, and you can Google the links here and get a more complete presentation about the topic. So in this circuit, we have, first of all, common source inductance, which is the inductance that is in common with the power loop and the gate loop. We have the power loop inductance, which is from the bypass capacitors to the high side device, down to the low side device, and back to the bypass capacitors. And we have the gate loop inductances, which is different between the turn-on, because it includes the bypass capacitor of the gate driver, and the turn-off, which doesn't include the bypass capacitor. So, talking about the impact of the common source inductance, this inductance is creating voltage drop in the gate drive voltage. So when the IDT, the variation of the current in the power loop, is creating a voltage drop in this inductor, the gate drive is affected. So the current switching transition is slowed down. And this has a huge impact on the loss of the converter because it's slowing down this transition. So you can see from the picture on the right, with even 100 picohenry of common source inductance, the effect is already visible. And of course, the loss increase is very high with very small parasitic inductance. Talking about the power loop inductance, the effect on the losses is less marked compared to the common source inductance. So it's not it has not a real big impact on the switching losses. But what happens is you create a lot of ringing during the switching transients, and this is creating two side effects. One is the higher overshoot, so you will need an higher ratings for the VDS on the device, and also the EMI is affected because those ringing in the switching node and in general in the in the voltage nodes of the converter is radiating EMI. If we overimpose the common source inductance effect on the loop power loop inductance effect, you can see it has much bigger impact. Then regarding the gate loop inductance, the effect is of an increased gate loop inductance is to create an overshoot in the gate drive. So basically, the circuit of the gate drive loop is based on the gate resistor, which is either internal to the gate driver or an additional external resistor, the inductance, the parasitic inductance of the gate loop, and the input capacitance of the device. And this is an RLC resonant converter, resonant circuit, and it can create overshoot on the gate of the device. So to limit this overshoot to our maximum ratings of 6 volts, you need to increase the gate resistor to dampen this resonance. So the higher is the gate loop inductance, the higher needs to be this resistor. So, and this basically slows down the switching. So it's also important to reduce the inductance on the gate loop. To compare few layouts, this is a very common, widely used layout. It's called lateral layout. So you have the two FETs, high side and low side, and the bypass capacitors on the side of the FET. So the current, the power loop currents are doing this path here. Second layout we are analyzing is the external vertical layout. So you have the bypass capacitors on the other side of the PCB. So the path of the current is between the high side FET, low side FET, down through vias the PCB to the bottom side and back to the bypass capacitor. The third layout we are presenting is internal vertical layout. So in this case, we have the low side device and the high side device and the bypass capacitors on the same layer of the PCB, on the same side of the PCB. And the current loop is closed on the first inner layer of the PCB. So if we compare the three designs, in the first case, the lateral layout, we have a pretty large loop area. So we can expect a large inductance from this layout. It can be, the inductance can be reduced by ground plane on the first inner layer, but it's still larger than in other cases that we will see in the next slide. In this case, we are dependent on the thickness of the PCB. So if the PCB is thin, the area of the loop is smaller. In the internal vertical layout, we are independent from the thickness of the PCB, and the loop area is small. It's a little longer path, but the thickness of the PCB between the first layer and the first inner layer, the top layer and the first inner layer, is very small. So how is inductance approximately evaluated in those layouts? So we have this example, current path, which is going on this direction, going down in some other layer of the PCB and returning back. So in this geometry, the inductance is proportional to the length, proportional to the thickness, and inversely proportional to the width. So if we compare this long narrow design with shorter and wider design, the inductance of the short and wide design is much lower than the other case. So to provide some values, a good lateral layout with the ground plane underneath is here. So it's providing from 1 nanohenry to 1.2, 1.5 nanohenry, 1.6 nanohenry, depending on the thickness of the insulation layer between the top layer and the first inner layer. External vertical layout is dependent on the board thickness, and it can provide parasitic inductance above 1 nanohenry. The internal vertical layout with very thin insulation layer between the top and the return of 4 mils. The parasitic inductance is around 0.4 nanohenry. And of course, the thicker is the insulation between the top layer and the first inner layer, the higher is the inductance of the internal vertical. But still, it can be seen it is the best solution available. So it is recommended for high switching speed. So how to design this internal vertical layout? You have to place components on the same side and as close as possible to make it shorter. You have to use as many vias as possible to go to the inner layer for the return. The isolation between the top layer and the return layer needs to be as thin as possible. The vias needs to be spread, and also bypass capacitor. It's better to use multiple small capacitors instead of one big capacitor. And to be noted that the return plane here is required for the return of the high frequency currents, so during the switching transient, but it's not mandatory, needs to be sized to bring the full current of the converter. As alternate layout configurations, we can place the bypass capacitors on the close to the low side instead of the high side. And in this case, the return of the power loop in the inner layer is the V-bus. And this can provide some better cooling of the high side device. And also an alternate layout with the bypass capacitors in the middle. In this case, the return is the switching node, and it can provide some shielding of the switching node since it is laid out in the first inner layer. Regarding the gate connection, the gate driver is depicted here on the left. You have the gate drive tracks, and you need to have the return on the first inner layer. So the return of the gate drive is always the net connected to the source of the driven device. So in this case, on the high side, it's the switching node. On the low side, it's the ground. So you can see on the first inner layer the return path for the gate drive. And also from this layout, you can see the current path of the power loop currents is orthogonal to the gate loop currents. So this will keep them well decoupled and reduce the common source inductance. Regarding the connection to the gate driver, we have multiple source terminals in our devices. And the correct way to implement Kelvin connection to the gate driver is the following one. So you need to connect all the source pads to the power loop, because all of them are responsible for the controlled current conduction. You need to place one or more, if possible, more vias close to the source pad, which is closer to the gate. and this will build the Kelvin connection to the gate driver. And again, the gate return polygon will be connected to those two vias here. And if you can see the current path from the gate driver, the gate drive current will go to the gate terminal and will return back from all the source terminals of the device, and it will go back to the gate drive. So there is some of common source inductance in this area, but this kind of layout is the best you can do. Final tips. You need to prioritize the layout of the switch. So in example, in a buck converter, the high side, in a boost converter, the low side. Then it's better to use many smaller capacitors to close the power loop. The capacitance is not important, might be between 10 and 100 nanofarad, because they just need to deal with the switching transit. Then the larger capacitors for dealing with the switching frequency ripple currents can be placed where convenient. They don't need to be placed very close to the power devices. In the power loop and gate drive loop, it's better to avoid unnecessary stuff. So only components that are dealing with the switching needs to be placed close to the device. One example I have is if you use a resistor from gate to source to keep the device off, that is just working in DC, so you can place it elsewhere and avoid that is placed and using space in a critical area. And also, you need to make sure that the components in the footprint library is correct for your application. As EPC, we offer Altium and KiCad libraries, and we have also a footprint drawing in the datasheet. And also, to not be overlooked, silkscreen matters. In some cases, if you surround a component with a silkscreen box, the flux flow during reflow is it's made more difficult, and this can have an impact in the soldering process, in the cleaning of the board after the reflow. So let's consider an example. As a case study, we have a very simple half bridge with a gate driver built around EPC 2218. So first consideration I want to say, on the input of the gate driver, it's almost always needed a filter to avoid coupling noise from the switching circuits to the inputs of the gate drivers. So this is especially true if the tracks from the controller to the gate driver are long or not very well shielded, or even more if they are coming from a separate PCB through a connector. So this is a good practice to have this input filter right at the inputs very close to the gate drive. Then let's have a look to common mistakes in the gate layout. So in this case, we have pad 2 of our device, which is the source pad close to the gate pad, used only as gate return. Then we have pretty thin tracks for the gate drive and the return. So basically, and we have also the return on the top layer only. So basically the gate loop currents are circulating in the top layer, and the gate loop inductance can be significantly higher. And also, in many cases, I've seen the high-side gate driver floating circuit, which is laid out over the ground polygon. So in this case, you have a significant coupling capacitance between the gate and the ground, which is equivalent to have an increased Miller capacitance. So how to fix those mistakes? So basically, we added the connection between the pad 2 and the other source pads. So in this way, we connect this pad to both the gate loop and the power loop. We increase the width of the tracks from 8 mils to 15 mils to try to reduce the gate loop inductance. We added a gate loop return polygon on the inner layer 1, and this is the polygon. And also this polygon is extended to stay below all the components related to the high-side FET gate drive circuit, including the bootstrap capacitor. Regarding power loop, we have seen pretty often this kind of errors. To place vias, too many vias, basically. And those vias are blocking the power loop return polygon. So as you can see here, the return currents from the low side are forced to go on this thin path here and in this thin path on this other side. So what you can do is to move those vias up here in example. So you can create those two additional paths that are also the most direct ones to the bypass capacitors. But then are those vias in the right position? So what is the purpose of those vias connected to the input bus? So those vias are meant to bring the DC current from the bus to the high-side device, because the bypass capacitors are already here. So the AC part of the current will be closed by the power loop return polygon here. So in this case, we can move those vias on the sides. And you can see we created a very direct path to the bypass capacitors. And also, those bypass capacitors can be moved a little bit down. And we can also use vias in pad to reduce further the inductance. Another example, how to parallel FETs for DC-DCs. So we have the same gate driver with, in this case, two parallel EPC 2218 driven by the same gate driver. So in this case, what we talk about is not two parallel devices, but we prefer to say that we parallel the half bridges. So in this case, we do a symmetric layout. We have more or less the same half bridge we were discussing before on the right, and we added another one on the left, which is symmetrical. So we had to rotate by 180 degrees the devices. You can see we optimized the layout of the high-side gate drive circuit with the hypothesis that this is a buck converter. So we prioritize the high-side drive. So we have the high-side gate driver tracks. So this is for the turn on and this is for the turn off. and those are going symmetrically from this point to the right side half bridge and the left side half bridge. On the low side gate drive, we had to do a little more of trade-off. So we have those two tracks going to the low side device, and then we had to route them on an inner layer to drive the other low side device. So you can see it is not perfect, but when you parallel devices, you always have to do some trade-offs, and this is why we recommend to use parallel devices only if the biggest device that we offer is not sufficient for your application. So inner layer 1, we used it for the high side gate drive return and for the power loop return. Inner layer 3 is used for basically low frequency, high current paths like the switching node, ground, and V-bus. So you can see here the switching node is collected in this area, so the inductor will be around here, and you can also distribute the ground and V-bus on inner layer 3. So you could see the source terminal of the high side device on the left leg is connected to the other source terminals only in the layer 3. Okay, let's talk now, let's have a look to the PCB parasitics. So this is not a complete guide to the PCB parasitics, but it's just to have some numbers in mind when you lay out a PCB. So the resistance of a copper path on a PCB, so this is the configuration. So it's a layer of copper of thickness T. We have two cases, 1 ounce copper, 2 ounce copper. And the resistance is independent from the side of the square. So we can talk about a specific resistance per square. So when you have a track, you need to put several squares in series between them and add the resistances. So in this case, with 1 ounce copper, the resistance per square is 700 micron. With 2 ounce copper is 2 times less, and so it's inversely proportional to the thickness of the copper. In terms of inductance, it is also a specific inductance per square, but the configuration is the one shown here. So you have a path and a return plane on the bottom side, and the thickness T is now related to the insulation between those two layers, insulation thickness. So for 0.1 millimeter insulation or 4 mils, you have 130 picohenry of parasitic inductance. If you double the thickness, you double also the inductance. And you have also a capacitance between the two, the top track and the return, which is 250 picofarad per square inch with 0.1 millimeter thickness, and it halves if you double the thickness. Regarding vias, they are a major source of parasitics because you can see typical via we are using in our design is roughly 2 million, and also thermally is 300 Kelvin per watt thermal resistance. So the vias we are using are via imped plated over. Typical drill diameter is 0.2 millimeter. The plating is 20 micron for IPC class 2 PCBs. And those parasitics are related to 1.5 millimeter length of the via. So basically the full width of the PCB in a 1.6 millimeter thick PCB. So those values are proportional to the length. So one suggestion is basically keep the via as short as possible. So connect to a neighbor plane, neighbor layer if it's possible. Regarding the inductance, via inductance is roughly 1 nanoair. Is not a precise value. It depends on the geometry and the return paths. But as a number, you can consider 1 nanoair. So it depends. So if you consider an example, a bypass capacitor connected with vias to inner layers, you can see from this table how the parasitic inductance depends on the via length primarily, and then also on the position of the vias. So in the end of the component, the inductance is larger, on the side is smaller, and also the smaller the component is, the lower is the parasitic inductance. So as usual, we need to keep the vias short. And also, if you are using vias in pad, there is this opportunity to place the via in this position, and this will also minimize the inductance also compared to the side placement of the standard vias. And also, if you can use 2 vias in parallel, it will be even better. Regarding how to use vias with EPC devices, we have now the QFN package. In example, the EPC 2302. We have 0.85 millimeter pitch between source and drain pads. So we can use the 0.2 millimeter drill and 0.35 or 0.4 millimeter annular ring diameter via with copper thickness up to 2 ounce, 70 micron. And also in inner layers, we can increase the annular link to 0.5 millimeter and handle up to 4 ounce copper thickness. It is also possible to use larger vias like 0.25 millimeter with 0.5 millimeter annular ring. Regarding chip scale package devices, we have 2 cases here. One is with 0.5 millimeter pitch, like the 2218 we were discussing before, or these other 2 very commonly used devices. The goal is to have 7 mils creepage copper to copper between pads. So it's challenging, but we have 3 options, let's say, those 3 options. So we can place vias only in source pads or only on drain pads. And the second option, we can interleave the vias, so place them in this zigzag position in order to allow to place them with the standard 0.2 millimeter, 0.35 millimeter via. The third option is to use smaller vias, but most likely this is an increase of cost, manufacturing cost of the PCB. Regarding our chip scale package with 0.4 millimeter pitch, an example EPC 2206, this is even more challenging, and most likely the standard vias cannot be placed in the pads. So we have for example, this kind of configuration here, in which we have the pads of the device are separated into sections, one upper and one lower. So we can place the vias in the middle, but we have to create this notch, which is only 7 mils wide. So the layout of 0.4 millimeter pitch devices is not trivial. Okay, let's have a final look at what are the differences between motor drive layout and DC-DC layout. So let's start from the main parameters of a motor drive. So in terms of current, DC-DC, we have converters from 5 to 100 amps. Those are typical values. There can be exceptions. Above this value, we usually suggest to increase the number of phases of the converter. In a motor drive, we start from, we have higher currents. So we start from about 20 up to 400 amps and more with multiple parallel devices. In terms of switching frequency, DC-DC, it's almost always above 200 kilohertz with GaN. And for motor drive, we switch usually between 50 and 200 kilohertz, depending on the application. Of course, if the current is larger, the frequencies is typically smaller. In terms of switching speed, the IDTs are between 5 and 20 amps per nanosecond for DC-DC and between 1 and 10 amps per nanosecond for motor drive. And the current transition times are few nanoseconds for DC-DC, while for motor drive, they are few tenths of nanoseconds. Also, in terms of DVDT, DC-DC, we are up to 100 volt per nanoseconds. Motor drive, we limit the DVDT between 2 and 10 volt per nanoseconds. And also voltage transition time, few nanoseconds for DC-DC, tens of nanoseconds for motor drive. That time is also longer with motor drive, while it is kept the bare minimum for DC-DCs. And switching losses are a significant fraction in the DC-DC application, while they are lower for motor drive. So from this table, we can understand that motor drive switching is about 1 order of magnitude slower than DC-DC switching. So these can be used at our advantage to simplify and optimize with a different priority our layouts. So let's start from the local high frequency capacitors. So those are much less critical because the switching is much slower. So they can be also omitted. And if you interleave the bus and ground layers on the PCB stack up, you will offer some local distributed capacitance that can keep the switching clean. The placement of the medium frequency or the bypass capacitors on the bus is less critical, so they can be moved where it's convenient. And also they can be placed in the opposite side of the PCB compared to the FETs. So we can say that the external vertical layout is okay for motor drives. Also, regarding the gate drive signals to drive multiple parallel devices, it's better to distribute them by shielding them with source return polygons. This is an example taken from our EPC 9186 board. So we have 4 parallel devices per switch, 2302 in QFN. So we have the low side device here, the high side device here, bus, switching node, and ground. And the gate drivers are on the left. So those are the gate drive distribution tracks for the low side and the high side. Those are in the inner layer immediately above the bottom layer. So you can see in the bottom layer, we have the gate driver here, and we have the return polygons, and also in the mid layer 7, so the next inner layer above the gate tracks, we have replicated the gate return polygons. So to be noted that in this layout, the power loop currents are mostly going vertical, and the gate drive currents are going horizontal, and this will reduce the common source inductance. Also, to connect the return polygons, we used a sort of Kelvin connection to avoid that the power loop currents are circulating in the gate return polygons. More layout for high current designs. So recommendation is to use a lot of vias. Stitching layers between them will allow the current to take alternate paths, and we reduce the overall PCB resistance. You need to take care of stack up. So usually heavy copper PCBs are used between, let's say, 6 and 10 layers, most likely 2 ounce in the outer layers and 4 ounce in the inner layers. This is an example of stack up we are using. So we have the power devices are in the top layer. We have the 2 ounce copper for routing on the top layer. And then we have the first 2 inner layers are 4 ounce, and those are dedicated to high current tracks, such as the switching node, ground, and VBus. Then we have 2 additional layers that can be used for routing in the center of the PCB. And then we have additional 4 ounce layers for distributing the VBus and ground and the switching node. The other recommendation is to avoid that tracks or other features in the PCB are creating cuts in the polygons. So in this picture, we have, let's say, moved from this solution on the left, which had some routing tracks cutting the VBus polygon go to the half bridges. So we moved those tracks in a different layer in order to keep the integrity of the distribution polygon for the VBus. Also, you can use PCB tools to estimate resistance or voltage drop and optimize the layout. Also, priority is the resistance of the path between the VBus, phase output, and ground. And this has higher priority than the low inductance power loop return. To be noted that the switching node is carrying the full current of the phase of the motor, while VBus and ground are carrying the same current, but half of the time. So those are the paths that needs to be optimized. So from input bus to output phase, and from output phase to ground. And to provide an example how we prioritize the low RDC, we are working on a layout in which we are repeating the same polygons in all layers. So we have the switching node, ground, and bus in order to use as many layers as possible for the high currents, except one for the power loop return. So this power loop return can also be moved in an inner layer in order to make the vias shorter and allow a better utilization of the inner layers for the high currents. Okay, so presentation is over. We summarize the topics. So we discussed 3 important layout-related parasitic inductances: common source inductance, power loop inductance, and gate loop inductance. We presented the best layout designs, internal vertical for the CDCs, and how to parallel FETs for the CDCs. Then we provided some hints, some tips for the PCB design and via design with EPC FETs. And we highlighted the different priorities for motor drive design comparison with DC-DC applications. So those are additional resources you can have a look to get a more thorough explanation of the topics we touched. Okay, thank you for your time, and I think now it's the time for questions.
Thank you, Tiziano. So now we are going to begin answering the questions submitted during today's presentation. As a reminder, you can still submit questions by typing your questions into the Q&A feature at the bottom of the screen. Tiziano, our first question is, what are the symptoms of gate voltage overshoot? So what will be the typical failure?
Okay, yes. Our devices have a maximum of 6 volt rating for the gate. And for correct operation, the gate drive voltage needs to be between 4.5 and 5 volts, better 5 volts. So there is a tight margin between the maximum absolute ratings and the nominal gate drive voltage. When you have an excess of gate loop inductance, you can get an overshoot of the drive voltage on the gate if you don't dump this resonance circuit with the proper gate resistor. And you have basically exceeding voltage on the gate. This is shortening the lifetime of the device. You can see, you can have a look to reliability report 16, an example. And there is, maybe we can try to open it. Okay, so there is an explanation in reliability report 16 regarding this VGS stress. And there is a nice plot. Here it is. Okay, so you can see this is 10 years lifetime of our device. And those are mean time to failure versus gate voltage. So you can see at 7 volt, you have several centuries of mean time to failures. At 8 volts, you are reduced to about 10 years. At 9 volts, you last most likely a couple of months or less. So this is what you have to expect when you have an over voltage on the gate. So it is important to check the gate voltage signals against over voltage. I have to say this test here is done with continuous DC voltage on the gate. In case of transients, the duration of the stress is much more limited. So most likely this lifetime estimation here is much more pessimistic compared to the real case. So I hope to have a reply to your question.
Thanks, Tiziano. Next question is more basic question. Which GaN technology EPC is using? Is it Schottky gate structure or GIT or Cascode or any different structure?
It's Schottky gate structure, and the advantage is you have the drive is dependent on the voltage, so you have just to charge the capacitances on the gate. So compared to GIT, you don't have to provide any bias current. And compared to Cascode, the structure is monolithic, is simpler, so is lower production cost, and it's also performing better. You cannot think about a cascade structure because of the parasitics of the structure itself with the speed of our GaNs. So it's the Schottky gate technology is what we are working on since several years, and I believe this is the best option.
Thanks, Tiziano. Next question is, can you highlight again why the source induction increases power loss? Is it an inductive and not a resistive parasitic?
Let me bring back the slide. It is just like this. Okay. Post slide. This one. Okay. Okay, let's consider that you need to turn on Q1. So the gate is at 0 volts. The gate driver transition to 5 volts. The device Q1 moves from 0 amps current to higher current. So the current in the device is increasing. So you have variation over time of the drain current, and this variation over time of the drain current is the same current is going in the common source inductance, and this DI/dt is creating a voltage drop on the common source inductance. This voltage drop is counteracting the gate drive voltage. So it's like to have a local feedback on the gate loop, which reduce the current drive capability of the gate driver because it introduce an equivalent voltage drop, which is equivalent to a higher value gate resistor. So the effect of the common source inductance is a strong reduction of the switching speed of the current. So this is increasing the overlap time and is increasing the power loss, the switching power loss.
Thanks, Tiziano. Then we have one question regarding competitive testing. So can I make a DIY TO220 packaging for the EPC GaN for some sort of comparative testing against MOSFET using the same board topology like DPT or half-bridge?
Yes.
So, shall I need to worry about parasitic inductances since EPC GaN packaging is so small and the routing is very difficult?
Yes, the answer is yes. Of course, it is a big trade-off, but it is possible, and some customers did it. And the point is, you need to have not a TO220, but you need to have a TO220 by 2 half bridge. So you need to have a single PCB with the half bridge on it. On that PCB, you need to place the small bypass capacitors, so few tens of nanofarad. That's it. And on the same half bridge board, you need to connect the gate and the source to the gate driver in a Kelvin way. So you cannot have, let me, So you have the TO220. So you have the other TO220 of the half bridge. And inside there is the EPC GaN. So this needs to be a single PCB. Okay. You need to have the bypass capacitors on this PCB somewhere here. Then you have ground, so gate, drain, source. So you have gate, drain, source, gate, drain, and source. And this will be GND. This source will be GND. This drain will be the bus. This drain will be switching node, and this source will be switching node. Okay, you cannot connect, you cannot use this terminal here and the source here for gate drive, because you will have a lot of common source inductance in the order of tens of nanohenry because of the pin of the TO220. So what you need to do is better to have the gate drive signals up here, gate and source, and use a twisted pair or a small coax to connect to the gate driver. Okay, so you cannot use this for gate drive. Those are the power loop connections. Up here, you need to place the gate loop connections, and this is a Kelvin connection, is a low common source inductance, and again, it's low common source inductance, but being wiring, it's high gate loop inductance. So most likely, you need to use a much larger gate resistor. So if you do an optimal layout, you might go down to 1, 2, 3 ohm gate resistor. With this kind of layout, you need to think about 10, 20 ohm of gate resistor. So you basically slow down the switching. So it is a big trade-off. It can be done. It is a big trade-off. I would do it just to evaluate initially if I have an existing design, to evaluate initially if there is some advantage. But when you do a proper layout like we explained before, that is the real game changer, and you will see much lower switching losses. Okay.
Okay, then I think we can do maybe 2 more questions. So one is, in high-frequency soft-switched converters, certain silicon devices have shown loss in COSS even with full soft switching. Is there such a mechanism in EPC devices as well?
We have not seen significant COSS loss in zero switching zero voltage switching converters. So I think there is no equivalent mechanism, and also the capacitances are usually smaller. I've seen that kind of increased loss in the COSS in some design of super junction silicon MOSFETs. I think it is a topic some manufacturer has addressed recently to bring back the COSS losses to negligible. But in our case, we don't see such a loss. We have examples of converters running at several megahertz in zero voltage switching, and also tens of megahertz in zero voltage switching. And we have not seen such an excess loss due to the COSS.
Okay, and last question for today's Q&A. Internal GaN diode usually is poor in performance. Is it recommended to add external diode between source and drain?
Okay, poor in performance in terms of voltage drop. It's very good in performance for switching, because we don't have reverse recovery. In terms of voltage drop, it is between 2 and 3 volts, depending on the current of the operation. It is possible to add a Schottky diode to help the freewheeling during the dead time. But what we recommend the most is to reduce the dead time as much as possible. And it is usually possible because gate drivers for GaN are very fast and they have very consistent propagation delays. And also the switching speed of our devices is very fast, so you can get the dead time down to 5 or 10 nanoseconds in some cases. Vice versa, when this dead time reduction is not possible, it is possible to use a Schottky diode that needs to be rated for the peak current. So the peak current of the Schottky diode needs to be rated for the full current of the converter, because it will be used only for the dead time, and the dead time is going to be a small fraction of the cycle. The drawbacks of adding a diode are two. One is somewhat increased capacitance in the switching node. Is not a big deal, maybe 10 or 20%. And the other drawback is when the Schottky diode is pushed hard, it still exhibits some sort of recovery. So it's not as perfect as the, let's say, the integrated diode of our device, the freewheeling mode of our devices. So, but it's depending on the application, it might be used.
Okay, thank you, Tiziano, and thank you everyone for attending today's webinar. So if we did not have the chance to answer your question, we will reach out to you with a response. Likewise, if there are any additional questions, please send them in to info@epc-co.com. I repeat, info@epc-co.com. You will receive a follow-up email within 48 hours with a link to the view of a recording of today's webinar. And you also can register to our next webinar, Revolutionizing Audio Amplifiers, Unleashing High Fidelity with EPC GaN FETs and ICs, also presented by Tiziano on the 7th of May at 10 a.m. Central European Time. And you can register on our website, epc-co.com. Thank you for joining us today and enjoy the rest of your day.
Thank you. Have a good day.
Bye-bye.